In this video, I'm going to show you a formal step-by-step method for writing the Lewis structures for molecules. You may recall from writing the Lewis dot representations of atoms that those can be combined to make simple molecules like CH4 methane. So imagine you have the Lewis dot representation of carbon showing its 4 valence electrons. It has 4 open positions it needs to share in order to complete its valence set of 8. Hydrogen has 1 valence electron, so if I take 4 hydrogens with its 1 electron and combine them, sharing those electrons with the carbon, now carbon has a complete valence shell of 8 electrons, in other words it's octet. Each hydrogen in return gets 1 electron shared from the carbon to complete the duets on the hydrogen atoms. Those pairs of electrons shown are usually rewritten as a single line, the 2-electron bond, like so. So this is a easy, simple method for writing out a Lewis structure for a molecule. It does a nice job of representing in a pictorial fashion how each bond is a shared pair of electrons between the atoms. However, it doesn't work as well, or is at least prone to error, if you try to apply that method to a more complex molecule like CO2, which has this Lewis structure. So trying to go from these Lewis dot representations to that Lewis structure usually ends up in mistakes. And it's even worse for nitrite, NO2-, starting with these Lewis dot representations and trying to get to the correct Lewis structure, which is this, is prone to error. So how do you go from those Lewis dot representations to that molecule? Well, since that method doesn't work very well, there is a different method, a formal step-by-step method that works for all molecules. And if you follow these steps, you'll come up with a correct Lewis representation for molecules every time. We're going to start, actually, as an illustrative example, with that simple methane molecule, just to show the first steps in this method. So what you're going to do is you're first going to write a skeleton structure . Do this for the molecule by arranging, the symbols of the atoms next to each other, so that you see how the atoms would be bonded together. So when you're starting out, it's hard to know what atom might be the central atom or how the atoms will be connected into the molecule till you gain more experience. Often you'll be told in the problem that such and such atom is the central atom and that the other ones are the other atoms are arranged around that central atom. In this case, carbon is the central atom, and we'll arrange the other atoms around, the hydrogen atoms around that carbon. So this is the start of our skeleton structure. Then what you're going to do is you're going to count valence electrons, and then you'll compute the total number of valence electrons . Okay, for the whole molecule. And the valence electrons are counted by looking at the number of valence electrons for each atom that is in the molecule. So in this case, carbon comes in with its 4 valence electrons. Hydrogen has 1 valence electron. And since there's 4 hydrogens, there'll be 4 electrons total from hydrogen atoms. We combine those to give the total number of valence electrons that we'll use to make the molecule. Next, you're going to complete your skeleton structure . And you'll do this by adding 2 electron bonds between each atom in the structure. So in this case, we're going to have bonds between carbon and the 4 hydrogens. We'll write lines to represent those bonds. Remember, each line represents a 2 electron bond. Next, we're going to subtract from our valence count the number of electrons we used in that skeleton structure. So subtract electrons added in the skeleton structure from the total electron count. So we had 8 electrons. We added into the skeleton 8 electrons. That leaves us with no electrons left. And so we're pretty much done with this molecule, and you can see it looks like the previous molecule that we wrote for methane. The last thing that you're going to do is to check octets and duets for the atoms for which those apply. In other words, carbon requires an octet of electrons. It has to have 8 in its valence shell. It now has 2, 4, 6, 8 electrons from those 4 bonds surrounding it. So it does have its octet. Each hydrogen has 2 electrons from the 1 bond to each of those hydrogens, and therefore they have their duet. And so this molecule is complete. Let's try another example. NF3, nitrogen trifluoride. So we're going to start the same way. We're going to arrange our atoms in the skeleton structure. In this case, nitrogen is the central atom to which the fluorines will be bonded. We're going to compute the total number of valence electrons. Nitrogen has 5. Fluorine has 7. There are 3 fluorines, so that's a total of 21 valence electrons from the fluorines. Add those, we get 26 valence electrons for the molecule. Now we'll complete the skeleton by drawing single bonds between the bonded atoms, the nitrogen and the fluorines. We'll subtract electrons that we've now added in the skeleton because we should total around the molecule we'll have 26 electrons. We've used up now 6 of those from the 3 bonds. So we need to subtract those 6 from our count. That leaves 20 electrons. Now what are we going to do with those 20 electrons? They have to go into the structure. Well, the next step is to add remaining electrons as lone pairs, in other words, unbonded pairs. And I'm going to give you a little advice. You'll have less problems if you set a priority to put those lone pairs around the terminal atoms and or the most electronegative atoms first. So when I start adding lone pairs from my remaining electrons, in this case I'm going to start with fluorine, because fluorine is both the terminal atom and also the more electronegative atom between nitrogen and fluorine. So we'll add 2, 4, 6. We have to stop there, right? Because now that fluorine has 8 electrons and it can't go beyond that because fluorine must have an octet. 2, 4, 6 around the second fluorine. That's 6 more around the third fluorine, so that's 18 electrons total in lone pairs. We can't add any more around fluorines because they can only have a total of 8, and each one of those has 8 now. So the last 2 electrons go with nitrogen. Finally, we check the octet and duets. We see that nitrogen and fluorine both have a total of 8 electrons. And then as a last check, it's a good idea to just count up the total electrons on the molecule and make sure it matches the total number of valence electrons that you originally counted up. So if we look at all the electrons in the molecule, we find that this has indeed 26 electrons. And so we have the right Lewis structure. Everything obeys the octet, and our electron count matches the total number of valence electrons that we counted up in the beginning of the exercise. Okay, so let's go to one more example. Now before we can do this example, hydrogen cyanide molecule, we have to define the different types of bonds. And for now, we're going to categorize bonds according to three types. Single bonds, in which there is one shared pair between the atoms. Double bonds, in which there are two shared electron pairs between the atoms. And triple bonds, in which there are three shared electron pairs between the atoms. And I'm just using carbon here as our example. There can be single, double, and triple bonds between many other types of atoms. These different types of bonds have slightly different properties. For instance, the bond strength increases in going from single to double to triple bonds. Bond length, the distance between the atoms, decreases as you go from single to double to triple bonds. So in other words, the single bond is the longest, triple bond is the shortest. Okay. So now, our hydrogen cyanide molecule. We're going to write the skeleton structure with carbon as the central atom. We'll compute the total number of valence electrons. Hydrogen has 1 electron, carbon 4 electrons, nitrogen has 5 electrons, and so we have a total of 10. We'll write in the bonds between the atoms to complete our skeleton structure. We subtract those electrons from our count. That leaves us with 6 that we have to add in as lone pairs. Now remember, the priority was on terminal atoms and the most electronegative. In this case, we cannot add any more electrons to hydrogen because hydrogen is already surrounded by 2 electrons from that one bond to carbon. Hydrogen cannot have more than 2. Nitrogen is more electronegative than carbon, and it's a terminal atom, so we're going to start by adding those 6 remaining electrons as lone pairs around the nitrogen. Now, that leaves us with no electrons. If we check octets and duets, we find that nitrogen is great, it has 8, but carbon is deficient. It has only 4 electrons, and it needs an octet. It needs 8 to complete its valence shell. So we're going to add a final step in our list of rules, which is we're going to use the lone pairs to complete any deficiencies of electrons. So any electron deficiencies that we see, anything that needs an octet and doesn't have it, we're going to complete those electron deficiencies by moving those lone pairs and forming double and triple bonds. So nitrogen can share 2 sets of lone pairs with a carbon. And that makes 1 new bond. Erase that. And that pair is moved in to make a bond, and then the other pair will be moved in. Now notice in doing so, we now have 8 electrons around carbon. Nitrogen still has its 8 because in sharing, in moving those lone pairs, we didn't detach them from the nitrogen. It's just sharing them with the carbon. so it still has its 8. So now everyone's happy. Carbon has an octet, nitrogen has an octet from its 3 bonds and its 1 lone pair, and hydrogen has its duet. Finally, we'll count up the total number of electrons in the structure, see that there is 2, 4, 6, 8, 10 electrons, and so this is the correct Lewis structure.